Hi guys, welcome to GTN Abacus Learning. In the last session, we modeled this structure and determined its displacements and reaction forces under this loading condition. Today we'll be doing something different. We'll be focusing on obtaining axial stresses in a rod which is inclined at a certain degree to its horizontal, something like this. This is a rod which is inclined to the x-axis, forming 60 degrees. It will have two nodes, one here, one here. Let this be direction 1. Let this point be A and this be B. If we are given the area of this section as 400 millimeter square, Young's modulus as 210 GPa, let the length be 2 meters. The problem might be to find the axial stress at its cross section when this rod is subjected to some initial conditions. The initial conditions may be displacements. For example, let node A be subjected to a displacement of 1/4 mm in the x direction and 0 mm in the y direction. Similarly, the point B can be subjected to initial displacement of 1/2 mm in the x direction and 3/4 mm in the y direction. So under these initial conditions, the problem might be to find what is the axial stress in this rod. Now to solve this theoretically, when you look into your lecture notes, you'll find that your stress, which is axial in direction 1, will be equal to where L is the cos component of the inclination to the x-axis, which is 60 degrees, and M equals to sine component, and this is the displacement vector, where U equals to, after you substitute all these values to this equation, you'll obtain your stress as 81.33 MPa. That's your axial stress under this loading condition. Now what we'll try to do here is model this in Abacus and see what we get. Today we'll be making 3D elements rather than 1D element. For this, we go to Parts, click on 3D, Deformable, Solid. We can name this as a rod. Keep this at 200. As you see here, Abacus has its own CAD, which allows us to draw various shapes and various geometries. In this problem, we're just given the area. We'll be making a rectangle, which is easier. So you click on rectangle, click here, just make a section, and to dimension its boundaries, you click here, add dimension, and click again, input your dimension. Let's make it 20, and let's make this one 20 as well. So the total area here is 400 millimeters square. Click done. Now that's your length of it. So the length here is 2 meters. So we'll put 2000. So now this is your 3D element. And now we have to assign the materials. So for this we go to materials, make this as steel, go to mechanical, elasticity and elastic. In the problem we are given 210 GPa. Here we write in MPa, so 210,000. Now just keep position ratio as 0.26 and click OK. And now we create our section, steel section, solid, and just select your material type, only have one for now, that's steel, and click OK. And now we go to parts again, go to rods, and we assign our section. So that's steel section, click OK. Once assigned, it will show our color. Then the next step would be to mesh it. So go to mesh. In here you'll find different options, but I won't be going through all of them today. We can just click on seeds. That's the size of your one single element you'll be forming within this whole domain. You can make it 50 for now. Click apply, OK, and then click on mesh, part, and click yes. Now we have to go to assembly and click here to bring your part, that's the rod part, click OK. Now let's transfer this rod to the center of our space. Click here. The endpoint, you can see here that it is already assigned as 0, 0, 0, so you can just hit enter to just translate that to the center of the space and click here. So what we'll do here is we'll rotate this rod by 60 degrees with respect to the x-axis. So for this we have to zoom in and select our axis of rotation. So this will be our axis of rotation, and the angle will be 60 degrees. Click enter. You can see here now it has been inclined by 60 degrees. Now let us create our step. Static, general static, like last time. Let's see our field output. What you want to see here today are the stresses, so it is already checked. Click OK. Now we go to boundary conditions. So in the boundary condition we have condition at A, where we have to specify our displacements. Click continue. This is our end A, so you select this end, click done, and we assign our displacements here. Now please note that we have different axes here as compared to our problem. That's x-axis, that's y-axis, but here that's our z-axis and that's our y-axis. u1 refers to displacement in x-axis, u2 displacement in y-axis, and u3 displacement in z-axis. So here in the z-axis we'll put our displacement as minus 0.25 mm, because in our problem we are given that this displacement here occurs in positive x-axis, which is negative z-axis in our model, and u2 will be 0. So click OK. Now let's assign our another boundary condition, which will be boundary at B. Click on continue. So zoom in our B end, click here, click done, and we assign our displacements. In U3 it will be minus 0.5, and in U2 it will be 0.75. Click OK. Here it will give you the direction of your displacements. Alright, now you can save your model and you can just create a job. This is rod at an angle. Click continue. OK, and submit this job. You can monitor, dismiss. Let's see our results. Okay, just go to stresses and maximum principal stresses. Let's run it. If we go to the end, we find that this rod has been subjected to a stress of 81.33 MPa. Please also note that we have meshed this section by 50 millimeters. Now if you go to our solution that we obtained through our calculation, we see that it is also 81.33 megapascal. Now let's go to assembly again. Let's change our meshing. Go to part, rod, mesh. So you can go to seed and part, or you can just click here. Let's make this one now 10. Now we've finally meshed it than before. Now I can go to job again and create a new job. Okay, submit this. Dismiss. Now you see here our stress value was 81.33, which has been changed to 81.6 in this finely meshed value. So our accuracy of the solution changes depending upon our meshing. You can see our reaction forces here and here. If you want to see the values right across the rod at any point, you click on tools, go to query, or you can just click on the eye symbol here and go to prop values. Now when you hover over the rods, you'll be able to see the value. Since it doesn't calculate the reaction forces here, it won't show it, but let's go to the stresses. Now you can see your values here. That's around 81.4 to 81.5. And let's see what is our maximum value. So go to options, contour, limits, and click on show location. So our maximum will be 81.6 MPa. Click apply. So that's our maximum here at this end, which is around 81.6 MPa. If you want to see your rod being stretched more clearly, You can change your scale factor. Just make it 500, apply, and you can play this. You can see it moving and stretching a bit. Now let's plot our stress values. Go to field output, continue. For the stresses, you have to go to integration point because stresses are calculated on a certain area. Click on stress components. Let's get our maximum principal. Add it. You can select this element here and click save. You can rename this one as stress at A. Let's select another point, which is stress at B. Save it. B. Again, let's select one more point in the middle, somewhere in the middle. At middle. Now let us plot these values here. B. So you can add these values to this plot as well. So you right click and say add to plot. You right click, say add to plot. They are all similar. What you can do here is that you can obtain your strains. Let's click on one of the values here. We'll go to strain components, max principal. So you can click on selection, click on this one and save it. So that's your strain at A. Here you can see our strain, which is linear because we are doing a linear analysis. Now to plot a stress strain curve, go to operate on XY data, click on combine, and you can click our x-axis, which will be strain at A, comma, and then stress at A, and then you can plot expression and see, and you can save it. So this is our stress strain curve. So today we learned how to model a rod using 3D elements, and we learned about meshing as well. We saw that given the finer mesh shows a different result than the coarser mesh, but the finer mesh gives us the more accurate result. And we learned how to operate on our XY data to obtain the stress strain curve. We also found that the value given by ABAQUS is equal to the value we obtained through our theoretical calculation. In the next session, we will be looking at process, which is assembly of these rods which are oriented in different angles to the x-axis. Thank you for watching till the end. Please comment, share and subscribe to this channel. Thank you.